Hi, we're going to solve a problem regarding cycles. This is related to chapter 2 of your thermodynamics book. In this example, a gas undergoes a cycle, and we have these three processes. As you can see, in process 1 to 2 we have constant volume. In the second one we have expansion with constant PV, pressure times volume, and in process 3.1 we have constant pressure. There are no significant changes in kinetic or potential energy, and we want to have these four desired information. The first one is we want to find this sketch of the cycle. We want to find the PV diagram. To do so, as we go back to the question, it says process 1-2 is at constant volume. We have the volume and we have increase in the internal energy, so it means that we have internal energy increase, so the pressure should go up, or we should see increase in the value of pressure to point 2. We don't know what exactly pressure at point 2 is, but we know that it's increasing. The volume is constant and the volume at point 1 is 0.028, and this is PV diagram. The next step is process 2 to 3. It says there is an expansion, so the volume is increasing, goes to the right, and with PV equal to constant. You know, curve like y equal to 1 over x looks like something like this, 2 over x something like this. So in general we can draw P versus V in a similar pattern. As it's increasing, so it goes to the right side with a similar pattern, as you can see here. So PV is constant and there is no change in the internal energy, so U3 is equal to U2. We don't know what exactly the pressure or volume of this point is, but when we go to the process 3 to 1, it says 3 and 1 have the same pressure, which is equal to 1.4. Then we know, okay, point 1 is at 1.4 bar. The pressure of point 3 is the same, so we have constant pressure, so we easily connected by this straight line. We have the work that is done on the system equal to 10.5 kilojoules, and this is our PV diagram. So this is the answer to the first question. In part B, we are asked to calculate the net work for the cycle. So what we need to do is we have to calculate the work at each step of our process, as you can see at each of these process paths, and then add them together in order to find the net total work of the cycle. For that, we know that delta KE, or kinetic energy, and potential energy are 0, as mentioned in the problem. In the process 1 to 2, as it says, because it's constant volume, the volume is not changing, therefore the work that is done in the path 1 is equal to 0, or in other words, as the boundary of the system is fixed, no work is done on the system or by the system, so we have W12 equal to 0. For process 2 to 3, we have PV equal to constant or polytropic process. This relation can be found from chapter 2, page 42 of your Thermodynamics Chapiro, Moran Chapiro book. This is the relation that can be used. P at point 3, volume at point 3, and Neperian logarithmic of V3 over V2. P3 is known, V2 is known, but V3 is not known, and we have to calculate it. Okay, but how to calculate V3? Look at this process 3 to 1. We have the work done, we have the pressure of these two, which is constant, and we know work is equal to P change in volume if the pressure is constant, because we have the pressure, we have the volume of the point V, or state 1, then we can find the volume of state 3. Therefore, we just write it down for this process 3 to 1. P times V1 minus V3. The value of work is known and it has negative sign here. The pressure is known. V1 is known, so we can find the value of volume at state 3, as you can see here. Now we can plug in this value into relation 1. P3, V2 were already known. V3 is known from this relation. Therefore, we have the work in process 2-3 as this value. You see, this is a positive value showing that the cycle is doing work in this process path. But if we want to find the net work for the whole cycle, we need to add them up. So we have W23 from here, W31 and W12 from the previous one. We know this value is 0. So this results in a value of 8.28 kilojoule as the net work of the cycle. And because this is a positive, this means that this work done by the system. Now the next step is to calculate the heat transfer for process 2-3. So from this point to this point, while there is no change in the internal energy and PV is equal to constant, we want to find what is the heat transfer. So we need to apply first law of thermodynamics, as you can see here. We know the net heat transfer minus the net work for this process is equal to change in internal energy, which is 0. We also considered the change in the potential energy and kinetic energy is equal to 0. Therefore, the net amount of heat transfer is equal to the work in this process. We had the work, we calculated the work to be 18.782 in the previous parts, and it's positive. Therefore, the Q, or the heat transfer, is in the system. Now in part D, we want to calculate the heat transfer for process 3-1, this process, which is happening at constant pressure. Because we are looking for the heat transfer in this process path, again we have to take advantage of first law of thermodynamics. We have the work, so we can write down Q minus W is equal to change in the internal energy, change in potential, plus change in kinetic and potential energy. These two are 0, therefore this difference is equal to change in the internal energy, which is U1, the final state, minus initial state, U3. And because we know from this process U3 is equal to U2, then we can write down Q minus W is equal to U1 minus U2. And if we look at this process 1-2, U2 minus U1 is 26.4. Therefore, U1 minus U2 is a negative value. We will have decrease in the internal energy if we go from 2 to 1. So we just write it down or plug it in from this value, minus 26.4 kilojoule. The work that is done on the system is 10.5. That's why it's negative. Then we plug it in here, minus 10.5. Therefore, from here we can find the value of heat transfer for the process 3-1 equal to minus 36.9. It means that heat is extracted from the system because it's a negative value, 36.9 kilojoules. Bear in mind that we didn't have any unit conversion or unit change in our solution so far. After solving the problem, if we are asked to see or to know if this cycle is for power station or refrigeration, our answer is we look at the net work of the cycle or the net heat transfer of the cycle. If these values are positive, if the heat is given to the system is positive, or if the work done by the system positive, we are dealing with power station. Otherwise, we are dealing with a refrigerator. Thank you.